The manufacture of photovoltaic modules begins with the process of growing silicon crystals. The crystals begin as rock-like pieces of silicon that are melted at 2,570 degrees Fahrenheit. A small silicon seed crystal is introduced into the molten silicon and slowly rotated, growing the seed into a single large crystal. Over the course of about 1 day, a cylindrical ingot, about 3 feet long and 6 inches in diameter, is grown. The top and tail of the ingot are cut off, and then the sides, to make the ingot more square. The scrap parts that were cut off are placed back into the crucible to make more crystals. The silicon ingot is then cut into thin wafers with a wire saw. Sawing thinner wafers means that more wafers can be made from each ingot, but thinner wafers are also more fragile. After the wafers are sawn, they are loaded into holders, cleaned, and etched. The etching process creates a texture of microscopic pyramids on the surface of the wafer, which helps direct more light down into the cell from many directions. More light absorbed by the cell means more electricity can be generated. The wafers are then transformed into photovoltaic cells. One side of the wafer is exposed to liquid phosphorus. The wafer is then heated in an oven to cause the phosphorus to penetrate into the surface of the cell. This process, called diffusion, turns the wafers into active cells. Next, electrical contacts are printed onto the front surface of the cell. A grid of very thin lines is printed on the cell. This leaves as much cell surface as possible exposed to light while allowing electrons to be conducted away from the cell. The cells are then coated with a special anti-reflective material that helps maximize the amount of light absorbed by the cell. The cell is then turned over and the back surface of the cell is coated with aluminum in a process called metallization. The cells are again heated in an oven, causing the aluminum to be absorbed into the surface of the silicon. Every single cell is tested under simulated sunlight and its electrical output measured. Based on the test results, the cells are sorted by machine into batches for use in different applications. The cells are then ready to be electrically connected to each other. Cells are connected using a state-of-the-art stringing machine. The negative side of one cell is connected to the positive side of the next cell, and so on, until a string of cells is assembled. After strings of cells are connected, they are transferred to a manufacturing area where robots assemble them into modules. A robot picks up strings of cells and arranges them into a complete module. After soldering the electrical connections, the robot lays the assembled strings on special tempered glass. A sheet of material called EVA is picked up by the robot and laid on top of the cells. EVA protects the cells against damage from humidity and UV light. The layer of cells between sheets of material is then laminated by being pressed together under vacuum at high temperatures. The laminate is then allowed to cool. Robots in the trimming area trim excess EVA from the edges of the laminate. This prepares the new laminate for framing. The laminate is framed with aluminum to give it rigidity and strength and to allow the module to be easily bolted to a structure, such as a roof. After framing, a junction box is mounted on the back of the module, allowing electrical connections between modules or to other components in the photovoltaic system. Robots then place the module on a conveyor belt that sends it to an automated testing area. Each module is tested, barcoded, and data logged into a sophisticated computer system. The photovoltaic modules are then ready to be shipped all over the world.